Hello, this is Professor Stephen Neshaba, and I'm here to help you out with part two, actually, of the computational lab. And this is we'll first start with the pre-lab part of this. So for this acid-base reaction, this is acetic acid combines with nitrite to produce the conjugate base and acid of those two, equation 12. You are to look up the values of the appropriate acid and base dissociation association reactions and derive a value of the equilibrium constant for that reaction 12. So the first part of that is table 17.2 that lists Ka values for various acids, including acetic acid, the CH3COOH, but it doesn't list the base Kb dissociation constants because that's just an acid dissociation constant table. But what you can do is use equation 13 that says the Kb for a base is equal to Kw, that's 10 to the minus 14, divided by Ka of the conjugate acid of a certain base. So we would be thinking, okay, Kb, I want Kb for the nitrite ion, NO2 minus. So you look up Ka for HNO2 in table 17.2, and then use equation 13 for that purpose. So now that you would have, and you might want to go ahead and do those and note them right now. Okay, so once you have Ka of acetic acid and Kb of the nitrite ion, then you can go back up to, let's see, equation 11 that says that for an acid-base reaction of the form that we were just looking at, which in this case in equation 10 is just written generically as HA, but that would be acetic acid and the nitrite ion there. The equilibrium constant for such a reaction is given by Ka of the acid, HA, times Kb of that base divided by Kw. So that's the theoretical underpinning of this. Now I'm going to switch over to Excel, and you probably ought to bring up Excel and, if you like, and enter in these numbers that I've kind of started here. As you can see, I've already entered in the values of Ka for acetic acid and for nitrous acid from table 17.2. Okay, assuming you're back, let's see what do we have to do here. Well, Kb for the conjugate base to HNO2, remember that was going to be equal to Kw, which is 1 times 10 to the minus 14, divided by the Ka. All right, so I have that number. And let's see, our equation for the equilibrium constant for that entire reaction, remember, is Ka times Kb divided by Kw. So that will be equal to Ka for the acetic acid times Kb for the nitrous, and all divided by 1 times 10 to the minus 14. And we get that value there. Okay, and the rest of this problem I think is going to be pretty straightforward, just a lot like we'll do problem part 1. I'll just kind of get us started on this. I've set up the initial conditions as the problem lays it out, 0.1 molar concentration for all 4 of those species, acetic acid, nitrate ion, going to the products. And here's our, this is the, I guess I could label this I, C, and E. Okay, there's our ice table. Here's my x variable. Now, since I've entered a value of 0 for x, then there's no change between these shifted values in the initial. But of course, if I put in some numbers here, then I would get something different. And so your task on this, of course, is to find the value of x for which this q value, which we've also entered, equals 0.044. And after that, you probably want to set up another box, which is the ratio between the 2 acid species. Okay, I think that should be enough to get you going on this one.